All right. So today we will introduce the third parallel language or library called the OpenMP, and it is also a way to do shared memory programming as we introduced before. And supposedly it's actually an easier way because it's supported by the compiler. We will introduce how to do the programming with OpenMP. Okay, so again, the OpenMP is a abbreviation for Open Specification for Multi-Processing. Okay, so of course, it's still a specification, an interface. So there are many other OpenMP library available for you to install on different system environment or type of operating system, or for InfiniBand or other network interconnects. Okay, and as we mentioned, this library is for shared memory programming, specifically for thread programming. Okay, and it's actually as the through this library you can tell the compiler to generate the code for you. So it's a very convenient way to do thread programming, or it's a very fast way to convert a program from sequential code to thread programs. Okay, and again, because it's a specification only, so well, it provides the portability to the programmer, right? And specifically for OpenMP, it supports C and Fortran, like many other parallel programming libraries or specifications, because in the past, the scientists usually somehow they use Fortran more for their code. So that's why you will find that many parallel programs or language, they actually support Fortran. Okay, and as we introduced, right, mentioning it briefly from the previous chapter, that the OpenMP actually follows strictly follow the fork and join model, right? So that means your program will consist of those sequential part and the parallel part. And when you reach those parallel part, or we say parallel region, then you will basically try to fork those threads from your main threads, so you can do the computation in parallel. But after that part of the code, then you will try to merge those threads back to the main thread or master threads. And the program basically keep repeating this pattern throughout the whole computation. Okay, as we also mentioned, right, because OpenMP is it's a solution from the compiler. So as you will see from this chapter in our introduction, the OpenMP only support very specific and just a few programming model or parallel techniques. Okay, that's why the compiler knows how to generate the code automatically for the user. Okay, all right. So the fork join model you can see from the figure below, right? So that's how a program supposed to execute. And as we mentioned, this is a compiler supported solution. And specifically, usually we call it compiler directive based. So compiler directive is, we will see it very shortly. This is a way to specify some directive in your program, and those directives is for a compiler. So the compiler knows how to write, for example, generate the code for the programmer. Okay. Okay, so before we talk about the detail, we can look at the example code quickly to see what is a compiler directive. And what kind of pattern could be generated or handled by OpenMP. Okay. And again, OpenMP is a library, right? So we have to include the library with our header files. And usually it's called omp.h. Okay. And then in your program, you will need to identify which part of the code can be parallelized. And as we will introduce, there are a few parallel pattern can be supported by OMP. And the for loop is one of them, okay, as you could imagine, right? So in this case, you can see we have a line added in our program, starting with a sharp symbol, right? So this, as we know, usually this is indicate this is the statement for the compiler, okay? And right, the argument we give below follows this symbol is our compiler directive, okay? And you can see contain several turns. We will explain them one by one later, okay? But it's not hard to imagine or understand that this basically means this is a pragma, means this is a compiler directive, and this is for the OMP library to use this library in your compiler to generate the code. And this will be what happened. What the coding block below will be a parallel region, as we mentioned from the fork and join model, right? And this parallel region will be is a for loop, right? So this is the pattern for your parallelism, and you're going to use 10 threads to basically execute this for loop in parallel, right? Okay. So pretty much it. So you can see there's not much to specify, and pretty straightforward. Okay. And because it's a region, right? So you can see by default it will be the next statement only. But because you probably want more statement to be included in a parallel region, so you can also use the bracket to indicate what's the starting point and end point of your parallel region, like we're showing here. Okay. So this is basically how you can use OpenMP to generate a parallel code. And as you can imagine, you don't see the code, right? You don't, because the code is generated, the binary code is generated by the compiler from your C program. Okay, but once you know how to do thread programming, it's actually not hard for you to imagine, right? What kind of code will be generated from the compiler, right? For example, here, basically, the whole parallel region, as you can imagine, will be converted into a function code, right? And then, the compiler will code, for example, pthread create API, right, for you, and pass this function pointer to that thread. So that thread can do this function, right? You can have many threads to execute this function in parallel. Okay, and of course the tricky part will be the management of the variable, right? Because you could have global variable, local variable, or basically you have to decide what's the data scope, right? Or how the memory variable will be managed across the threads. So that part is actually not controlled by or partly controlled by the compiler directives. Okay, so that part is actually the harder part for OpenMP programming, because you don't directly see the code generated from the compiler. So you must need to know some rule or some definition about how to decide the data scope of a variable when they get converted to the code. Okay, so that you can know so you can know exactly how the what will be the behavior of your variables. Okay, So that's part we will have after we introduce those how you specify those directives. We'll discuss about that. How to distinguish or how to determine what's the data scope of each variable in your payroll region. Okay. Right. So the OpenMP directives, not many, only a few, like we listed over here. So just as we explained it, right? If you use OpenMP, you always start with this sharp and then pragma OMP. Okay. And then what's follow that will be your directive. Okay. And for example, you have the directive of payroll, do, for, and a few more we will introduce. Okay. And for each directive, so each line basically is one directive only. Okay. And each directive could have many clauses. So those clauses are, you can think it as configuration, right? To determine how the directive will generate the code. Okay. So those configuration, of course, they have some default setting, and you can use clause to override them. And so those clauses are some optional configuration setting can be given by the programmer. Okay. And such as default and private, and we will talk about those later. And those are, are clauses to control the data scope we mentioned. Okay. So that's it. How you can specify a directive. You need to add those lines in your program, basically, for the compiler. Okay, and the rest of the rules, right? Case study of case sensitive, of course, it depends on the programming language. So if it's C or C++, then of course you have to still follow the case sensitive rule. So the name of the directive or the clause showing here, you also need to be careful about whether it should be lowercase or uppercase. Okay. And secondly, as we mentioned, one directive per line. There is exception for as we will explain. Only for can combine with parallel. Okay, so that's very few exception. Okay, and just for convenience for the programmer, so you don't need to write two lines. You can just merge them to in a single line. Okay. And finally is what we mentioned. The directive will be applied to a statement or a struct block, right? And it will be the statement within brackets. Okay. So the directive could be applied for a single statement by default, but if you have brackets, then you will apply to the whole region of code. Okay. All right. So now we just start introduce those directives. Okay. And now in OpenMP, we usually also code it as a struct. Okay. And we have those directives can be basically two type of struct. The payroll directive imply the payroll region construct. Okay. And the rest of the directive, they are all belongs to the working sharing construct. As you can imagine, the payroll region basically is a fork operation. So this directive will try to fork the threads for you. And then after you have the threads, how you decide to do the parallelization or how you distribute the workload, all those are controlled by the working sharing construct. And of course, there are a couple of patterns, right, you could use to do the work sharing. So manning will be the do or for directive, or the section and the single. So we will explain them later. Okay. And as all the shared memory programming, especially we talk a bit more in the previous lecture, synchronization is an issue, right? So OpenMP also have some construct for synchronization. And you will see that's pretty much very close to some of the synchronization API provided from pthreads. Okay, but is specified, by the compiler directive instead. Okay, and finally is the clause, right? Like we mentioned, and the most important clause are the one that try to override or define the data scope of your variables. And this will be crucial because that will certainly affect your results, right? Or even your efficiency, and determine whether you will involve a memory copy or you will just involve memory access. Okay. And finally is the library routines. There are only a few, and those routines are usually just for query the status or set some default configurations. Well, they are usually less important. Okay. All right. So let's start with the first directive called the payroll directive. Okay. And of course, this is the most important one because this is the one start your fork and join model, right? Because this is the only directive that has the ability to create threads or fork the threads. Okay, so that's why it's called the payroll directive. So the payroll directive also implies a payroll region. Okay, and so the size of the region will depends on your struct block, right? The bracket you specify in your code. Okay, so as I mentioned, right? So the payroll region, the payroll directive, all it does is to fork the threads. So you will fork a group of threads. Okay, and however, this is only thing handled by this directive or handled by the compiler. So after the thread is created, the function they execute will actually be exactly the same. Okay, so that's why usually we combine the payroll directive with other working sharing directive, because the working sharing directive will allow those threads to do different things, right? Like to explore data pair reason or other type of workload sharing techniques, okay, or programming pattern, okay. And so that's why we usually need to combine those two constructs together, okay. And since you create those threads, right, it's a fork and join model. So implicitly, you can imagine after the payroll region, all the threads will be joined together. And by default, right, we know join is a blocking code. So that means you actually have a barrier at the end of the payroll region. Okay. So if any threads that cannot finish or is still running, then all the threads have to wait for the last one, because you have a barrier at the end. Okay, at the end of this region. Okay, and as I mentioned, if there's if you have a value in between or exception, and that cause one thread terminate, then all the threads will be terminated. Okay? Because OpenMP does not know how to handle this situation. So one fails, all fails. Okay. Right. And another important thing you need to pay attention to when you write a code in the payroll region is that you need to imagine, right, this struct of block or this region of code will be converted into a function. So your code written in this payroll region should not, for example, jump outside the region, right? Because as we know, within the function code, you can only jump within the function, right? You cannot jump from one function to another. You have to make the function code. You cannot just jump, right? So some of the statement will not be allowed, or you must use it properly within the payroll region. You all basically just imagine the code in that region is a function. So whatever the code that can be executed by a single function, then that's fine. But if it not, if it cannot be run in a function involve a cross function, then that shouldn't be, you shouldn't do that. Okay. All right. So as pointed out here, right, a payload region must should not span outside a function code. Okay. All right. So once we know the purpose of a payload directive, then all he does is to create the threads. So the question will be, or the only thing you need to decide or control is how many threads should be created for this payload region, right? And there are many ways to decide the number of threads, and they will be determined in this precedence. Okay. So first is the if clause. Okay. So like the example showing over here, now after parallel, we can have an if clause, and of course, it should have a Boolean condition, right? And if the Boolean result is true, then it means it will create threads, but it hasn't decided how many threads yet. Okay. However, if the Boolean condition returns false, then only one thread is created, or you could say no threads is created. The function, the code in your payload region will simply be executed by the main threads. So basically, that means you can basically ignore the payload directive you wrote here. Okay, so that's the purpose of a if clause. Okay, and you decide whether it should really enter into a payload region. Okay, whether it will need to create threads. Okay, all right. So if you don't have a if clause over there, or if the if condition is true, then the next thing he tried to determine the number of threads is based on this number of threads clause for the payload directive, like the example we showed before, right? So clearly it will specify the number of threads is 10 for this payload region. So 10 threads will be created. Okay, all right. And if you don't specify the clause in this directive, then the OpenMP compiler can only try to see some default setting from your program, right? And the one way to set the default value is by the library function, the OMP set number of threads. Okay, so of course, this function you can give an argument, a number, right, to determine the configuration. Okay, so whenever you make this code, then you will override you will specify the default number of threads. So this setting will apply to all the payload region, right, after you make the changes. Okay, unless, of course, like we show over here, if you specify the number of threads clause in your payload directive, then this clause will override the default value. But this setting will only apply to this payload region only. But if you can imagine, in some case, throughout your whole program, right, you want to have the same payload region, and you don't want to specify this number of threads in each of your directives. So you might as well just simply call the set number of threads at the beginning of your program, and to set the number of threads to some default value, right? And you don't need to specify that in your payload directive anymore. Okay, so just make sure you code this before the payload region, so it will take effect. Okay, all right. So what if, right? So what if a programmer he doesn't even specify the number of threads through the library function? Then basically you can imagine for the compiler, it cannot find any information about the number of threads from your program. So the compiler has to ask the help from the operating system. So he will check the system environment. and specifically, he will check the OMP non-threats environment variable. Okay, so this is an environment variable, right, managed by the operating system. So as you should know, or you will know that basically just issue the command to set this environment in your operating system, and so it will affect the compiler. Okay. So when will we do this? Usually is we want the setting to apply on the whole machine, right? Across all the OpenMP programs. Then we will set this environment variable. Okay. For example, as you know, like our course, right? You use the cluster to run your job, right? So when your job gets scheduled on a node, then you control of the node to run your program. So one way is you can specify this in your job script, right? So before run your program, you can determine what the pair reason or how many threads you want to use for all the OMP program you run on that machine. Okay. Usually this is a setting controlled by the system administrator or the machine manager. Okay. All right. So finally, if even the operating system doesn't have any crew, no setting is given, then the compiler can only ask the hardware, right? So at the end, you will ask the operating system for how many CPU cores on this node. Then by default, it will use that to determine what's the how many threads should be generated for a parallel region. Okay. So basically that's the default setting. Okay. All right. So okay, so I think that should be clear. So in any case, you should be able to determine how many threads will be created for your parallel region. Okay. And for the parallel region, actually it also supported nested parallel region. For most of the OpenMP program or library, but may not necessarily all of them. Okay, so to be careful, usually you still want to check whether the library support nested parallel region. Okay, and the nested parallel region, as you can imagine, right, it's pretty easy to understand. Basically, that's a parallel region within another parallel region. Okay, and what happened is you can imagine like the case over here. You will actually create a total of 6 threads, right? 2 by 3. Okay, because you create 2 threads, and then within that threads, each of threads will create another 3 threads. Okay, so the total pair reason is actually 6. Okay, all right, and although here you can see the 2 parallel region, they are right next to each other, right? So after you have the pair, you specify another pair region in the first line of the outer pair region, but it's not a requirement. Okay, so you actually can specify a pair region in any part of the outer pair region. Okay, so you can basically you are allowed to create threads at any time. Okay, and those threads, of course, will get joined by the end of the parallel region, right? Okay, and so as we mentioned, right, sometimes you might want to check whether it's supported or not. So you do have some API allow you to, or some of the library routine let you to decide whether, for example, set nested means you enable this nested parallel region capability. Okay, so you could also, of course, turn it off. Then you will ignore the inner parallel region directive. Okay, all right, and you can use get nested to determine whether you are actually within the nested for parallel region or not. Okay, all right. So, and of course, if it's not, or it's a disabled, then like before, the directive will basically get ignored by the compiler. Okay? All right, so that's it for parallel directive. Okay, so then we will move on to the working share construct, which is of course the most important part. Okay, so as we mentioned, right, the parallel region or the parallel directive is the only directive that has the ability to create threads. So all the working share construct we introduced here, they do not fork any threads. All it does is to modify the code they generated, for the threads, and they were generated in a way so that your computation can be shared or distributed to those threads, right? So that's why you can your parallel code will have better parallelism and have speed up. Okay, and so as you can see over here, okay, different from the parallel region or working share, okay, it doesn't have a barrier, okay, at the end of the construct, okay, because it doesn't create any threads, so it doesn't need to join them as well. So by default, there's no barrier, okay. So whenever the thread complete the work it assigned from the work sharing construct, it will just leave the construct and continue to execute whatever the code in the rest of the parallel region. Okay. Okay. So okay, so that's his default behavior. Okay. All right. So that's the okay. So let's see. Oh, so sorry to make a correction. Okay, here. Okay, so when we leave the working share construct, okay, showing here, actually it does have a barrier, but for the entry point, there's not. Okay, the for the exit part, actually will introduce a clause, so you can use that clause to override that. So by default, there's a barrier at the end, but this barrier can be override by a clause. But for entry, no, to enter the construct, the working share construct, there's no barrier. So that means no, in a parallel region, whenever a thread complete their own code in the parallel region, they can whenever he reach this directive, he will just execute the function assigned by this working share construct. Okay. So there's no barrier at the beginning, but there's a barrier at the end. Okay. All right. So we'll only introduce three constructs, and they are pretty much sufficient for most of the programming. Okay. And so the first one is the do and the for. So as you can imagine, they are like the example we showed before, and they try to basically it's a data parallelism model, right? So that means supposedly you have a array or some data listed over there that can be processed independently, right? So that's what we call the data parallelism. And instead of process those elements one by one by a single core, so we want to create many threads to try to process those data elements at the same time in parallel. Okay, and of course you can use a for loop or you can use a while loop. Okay, so that's why you have do and for, those two constructs. Okay. All right, and the second type is sections. Okay, so the section basically try to parallelize the code itself, not the data. So as you will see, basically you will generate a bunch of branches. Okay, so you allow each thread to execute different function or different section of code. Okay, so as you can imagine, right? Because each thread will need to run its own individual function. So usually people, the parallelism of section shouldn't be too large. Otherwise, you have to write a bunch of codes. right? Because each thread should be, should execute different function. And usually we don't have so many, right, different actions for each of the threads, right? Just for a few cases, like the MPI, right, we have branch, so you can run the code for the master or for a slave. So in that case, section is right the construct you should use. Okay. All right, and finally is single, and single is actually a way to handle synchronization. Okay, and as showing over here, right, the behavior of a single is that remember it's still any work sharing construct should be specified within the parallel region. So supposedly you should have many threads to execute this construct. And the single is the one that try to actually convert the parallel region back to just sequential code behavior. So you will only ask one of the threads to execute this section of code, while the rest of the threads do nothing. And because, as we mentioned, you still have a barrier, right, at the end of the construct. So basically, those waiting threads will idle until the function is completed by the running threads. Okay, so it's a way to do serialization, basically. Okay. All right. So as we mentioned, of course, all those are have to within the parallel region. Okay. All right. So that's why a parallel directive could be written in the same line of any one of those working share construct. Okay, because supposedly this working share construct in most cases will be given right after the parallel region or the parallel directive. So for ease of programming, sometimes we can write parallel for or parallel section within one line. Okay. All right. So let's get a closer look at those directives. Okay. So the first one is the do or for directive. They are pretty much the same. So we just introduce for as example. Okay. And of course, right, the for will be applied on a for loop. So the statement right next to this directive must be a for loop. Okay. If it's not, then compiler will throw error. It doesn't know how to generate the code for you. Okay. Same thing, if it's a do directive, then you should have a while loop follow it. Okay. It's not too hard to imagine how to parallelize it, right? So basically, he will those directive will basically divide each iteration as a single task. Okay, and then dispatch those tasks to the threads you created in the parallel region. So eventually your task will be completed by some threads. Okay, and this directive or for directive will ensure that every iteration is executed by some threads. Okay. But remember those threads, right? They can execute in run in parallel. So that means the iteration from your loops will also be executed out of order, right? In parallel. Okay. So that's the default behavior. Okay. And for the for directive, there are some important clauses you would like to know. Okay. So the first one is no wait. So this is the one we mentioned that if you have this clause, then you will remove the barrier at the end of this directive. Okay. So but you're still in the parallel region. So as I mentioned, if you have no wait, then whenever there's no more task to be executed by the thread, then the thread will complete this construct and exit this region and continue to run the code for the rest of the parallel region. Okay. And schedule is the probably the most important one, and we will talk about that more because you can imagine this is the clause to decide the scheduling algorithm, right? How you schedule those tasks to a fixed or limited number of threads you created. Okay, and of course the scheduling algorithm will affect the performance. So you will actually use it and observe it in your second homework. Okay. And the third one is the order, right? So as we mentioned, by default, the task can be executed out of order in order to make sure, right, we explore the maximize our pair reason, right? However, for some use case, you might have to get the result from those iteration in order. For example, maybe you want to print out something from each iteration and you want to print out on your screen in the correct order. So in that case, you can use the order clause to force that. Basically, what happened is you can imagine the compiler will introduce some lock, and to make sure the first iteration must be finished before the second iteration finished. Okay. And so finally is the collapse, and we'll example to show that it's pretty much like nested parallel region. Here we could have nested loop, right? Many times we write a code, for example, for I and for J and for K. And so if there's no dependency between those three I, J, K loops, then you can collapse them together and flatten the task, so you can have higher degree of pair reason. Okay, so let's have a quick look at the option from schedule clause. Okay, so first thing you need to know is that we mentioned the task, right? So the iteration is bunch of computation, and those computation will be divided into tasks. And in fact, the definition of the task is decided by a parameter called chunks. So chunks is, you can think it as the number of iteration. Okay, so it's actually, of course, by default, the chunk size is 1. So one iteration is one task. But if your chunk size is 5, then that means every task will run 5 iterations. Okay. And of course, the iteration has an index, so it's not like any iteration. So maybe the first task is to run iteration 0 to 4, and the next task will run iteration 5 to 9. Okay. So for static, it's very simple. It's a round robin. Okay. And so, but you can specify the chunk size, so you can decide the degree of your task, decide how many tasks will be generated, right? And those tasks will just based on their iteration, their index, to schedule on those threads in a round robin fashion. Okay. So basically, because the number of threads is a fixed number, the number of tasks also determined by your chunk size. They are both fixed results. So the mapping between the tasks and the threads are right. The relation is a static. That's why it's called the static scheduling algorithm. Okay. So their assignment is basically predetermined. So actually, static is the fastest scheduling algorithm, right? Because you just compute and there's no runtime, decision to make. But however, as you will see in the second homework, you try to resolve the load balancing problem. So the problem is caused by the fact that for some use case, you handle the computation workload for each task are not the same, right? So you cannot just even the load by given the same amount of tasks. Okay, so that's why we need dynamic scheduling. Okay, so dynamic scheduling basically is right first come first serve solution. Okay, so again, you accept a chunk argument to decide how many tasks are there. Okay, but the mapping between the tasks and the threads are determined at runtime because whenever a threat complete a task, he assigned, he will ask for the next task to execute. Okay, so if you, assign a smaller task, you will probably handle more tasks at the end. Okay? And of course, in this way, usually it can result in better load balancing, right? And you can avoid the problem caused by the unbalanced tasks we mentioned. Okay. And for homework too, basically you will try those strategy because you are facing a low balancing problem. Okay. And we'll also ask you to implement this load balancing strategy on your own at the MPI level. Okay, so just a heads up for what will happen for your homework too. Okay, and the third option is guided. So the guided is you could say an improvement over dynamic in some cases. Okay, so the problem he tried to solve from dynamic is the fact that when we do the load balancing, because the scheduling decision is made at runtime. So if your chunk size is too small, right, that means you have more tasks to schedule. That means you have to make more scheduling decision at runtime. So every scheduling decision is consume some time. Okay, so there's a trade-off to decide the chunk size. If the chunk size is too small, if the chunk size is small, then you can get a more balanced result at the end. But at the same time, you may suffer from higher scheduling overhead. On the other hand, if the chunk size is large, then you don't do that many scheduling decisions, so the scheduling overhead is lower. But the chunk size is huge, so you may not, you have some fragmented computing workload, so your workload cannot be evenly distributed across all the threads. So there's a trade-off. So the guided one is the strategy that try to balance between the two. So basic strategy is at the beginning, it will use a larger chunk size, but at the end, it will, as your computation keep running toward the end, he will gradually increase the chunk size. Okay, so gradually actually reduce the chunk size, right? Because toward the end, you want to have a smaller granularity and make sure at the end you can balance the workload. Okay. All right, and finally, runtime actually seems more flexible, but it's actually worse usually because it's up to the compiler to decide which strategy to use, and usually compiler doesn't have enough information to make the right code. So auto is the one I mentioned, right? So auto is made by a compiler, so usually we don't do auto. And runtime is just use the system environment to decide whether you're going to use static, dynamic, or guided for this directive. Okay. Finish this and then we will before the class over. Okay. So here's some example just to make sure you know what's the meaning of those scheduling options. So you have the static. You can see that just simply a round robin strategy, and dynamic. You can see that you do not know the mapping between the tasks and the threads. And finally, a guided. You can see that if you look at the number of iterations in each task, right, you are from 10 reduced to only 5. So that's the purpose of guided scheduling. Okay. All right. So so we will finish the rest of the this chapter, okay, in our next lecture. Okay. All right. So is there any questions?